Now that we've seen how entanglement works, we want to build up our skills so that we can do some algorithms. So we're going to start out exploring a little bit more about phase, and I'm going to call this Fun with Phase. All right, let's look at a new gate. It's called the Z gate, and I think of this as the phase flip gate. So if we have a 0 ball, a white ball, it does nothing. But if we have a black ball, it changes it from positive phase to negative phase. Likewise, it also changes it from negative phase to positive phase. What we want to see is, like the controlled knot, what happens if we have a control on this. So there is, we remember the controlled knot, that as long as there is a white ball as the control, nothing changes. But if there is a black ball as control, then it flips the result. Okay, let's look at what a controlled Z looks like. And we'll start out by doing it with what our intuition would tell us. How should a controlled Z work if it works in a similar way as a C knot? And so what we would think is that it would only change the phase if the control ball is black. And that actually makes sense because look, so if the control is white, which is the left column, then the target doesn't change. If the control ball is black, then we apply a Z gate. But as we know, a Z gate applied on a white doesn't make any difference. So what we see is that the only time a change happens is when I have a black ball, and that changes from black to negative black or from negative black to black. All right, now let's look at what the math tells us about what's going on. So I have here the matrix for the controlled Z, and you can see whenever you see 1, 0, 0, 1 in a square, that means to not do anything to those. So with the ones down the middle, you see the first 3 choices, 0, 0, 0, 1, 1, 0, have no change, and the last one's going to be negative. So let's calculate this out and see. So in the first case, we start with a 0, 1, which is a 1 in the second position. And if we multiply it out, then we'll see that it had no change. Likewise, when we start with a 0, 0, that's a 1 in the topmost position. And that the result is 1, 0, 0, 0, which is also no change. Then we have our third choice, which is a 1, 0, 0, 0, 1, 0 on the vector. If we multiply this out, we'll get exactly the same as we started with. But then we come to our fourth choice. And what we notice is, yes, we have that negative sign as we anticipated, but notice that when we write this in bracket notation, the negative sign isn't in front of a single qubit. It's in front of the 2 qubit pair. And it turns out that either qubit could hold that -1 or that negative phase. So in this case, we have a phase that's being applied to a 2 qubit pair as opposed to a single qubit. This is going to be very important later. So you want to keep remembering this, that phase, when we calculate multi-qubit operations, phase is associated with a pair. And then we use our algebra, or the opposite of the tensor product, to pull out what are the possible qubit assignments that could multiply together to get this multi-qubit result. Okay. So what we really want to understand from this is that multi-bit operations aren't solved neatly with visual representation. There are limits to the visual representation, or there are some rules about phase that are not as clear when we use the visual representation. Okay? So phase is allowed to do more things than we think. It's allowed to wander. So phase is associated with 2-bit pairs, not just the single bit of a pair. And any mathematically correct separation to individual bits is acceptable. And we also learned that control gates, we already saw that C naught led to interesting quantum behaviors. And now we're seeing that the CZ gate also leads to interesting behaviors that are going to be more important later, this type of behavior.